Hi, I'm Sewon Lee from Seoul National University, South Korea. And now I'm going to present our work titled Reduce GCN. And in this work, we aim to alleviate the oversmoothing problem in graph-based recommendation. And this work is primarily led by Eunji Kim. Let's first start by explaining the main task here, the top N recommendation. It aims to recommend the top N items to each user based on their previous interactions. And widely used approach for this task is collaborative filtering. It typically finds similar users based on the common items they both interacted with. For example, if two users here, one with a red line and another with a green line, share many items in their histories, we consider them similar. And then an item one user hasn't seen, but a similar user has, can be recommended. And among many collaborative filtering methods, one effective direction is to use graph convolutional networks, or GCNs. Recommendation data can be naturally represented as a graph, specifically a bipartite graph where nodes are users and items, and edges indicate the interactions between them. In GCN-based recommender, user and item representations are updated by a process called message passing, where we aggregate information from neighboring nodes for up to k hops away in the data, in the graph. For example, without any message passing, each user representation is just their own initial embedding. And with one layer of message passing, the representation is updated by aggregating information from one hop neighbors, so the neighbors connected by just a single edge. Similarly, with two layers, it includes two hop neighbors and three hop neighbors with three layers. This multi-hop aggregation allows the model to capture broader context from the graph. However, there is a well-known issue here called oversmoothing. As we stack many GCN layers, most nodes get to be connected all together, and since they all share similar multi-hop neighbors, their representations become too similar, making it hard for the model to distinguish between them. This leads to a negative impact on model performance, especially in personalized recommendation tasks. And this issue is especially critical in recommendation data. The figure here shows the graph coverage, that is, how much of the graph is used when computing each node's representation with different number of GCN layers. When we look at the blue bars here, which are from the previous GCN-based methods, with just 3 to 5 layers, most nodes are already covering over 90% of the graph. And that's also why most existing GCN-based recommenders show peak performance with only 2 to 4 layers, not using the, Our key idea here is to solve this problem, reducing message passing from less relevant nodes or edges while preserving the important ones. To this end, we propose reduced GCN with two main strategies. First is a neighborhood reduction. Instead of using all neighbors, we selectively aggregate only the most important ones, reducing message passing on less relevant nodes. Second, in edge weight reduction, instead of using deterministic weights for all edges, we learn adaptive weights that reduce the influence of less relevant interactions. Together, these two techniques help the model focus on the most relevant parts of the graph, ultimately alleviating the oversmoothing. And this is the overall architecture of our model. The neighborhood reduction is performed at every epoch, and then edge reduction and message passing is applied on the reduced graphs at each layer. First, let's look into the neighborhood reduction. To selectively aggregate only the important neighbors, we need to know which nodes are semantically similar. So we cluster nodes into subgraphs, each representing a coherent subcommunity of users and items that share similar preferences. To do this efficiently, we use an anchor-based clustering. We select the anchor user in red for each cluster and build a cluster with similar users and items from this anchor in a bottom-up manner. The first step is to select meaningful anchors for each subcommunity. Since the anchors need to represent each subcommunity, they should cover as much preference as possible while not overlapping with each other. To achieve this, we first build a user graph where each node is a user, and the edges are weighted by the number of common items between two users. From this user graph, we select anchor users using a greedy algorithm, starting with the user node who has the highest degree. and then remove all the edges connected to it and repeat. For each epoch, we calculate the relevance score between these selected anchors and all nodes using the inner product of their initial embeddings. And if this score exceeds certain threshold T, the node is included in the subgraph associated with that anchor, and we repeat it for all the subgraphs. We then retain only the edges connecting nodes within the same subgraph. So instead of working with the full graph only, we construct smaller focused subgraphs. And note that nodes can belong to multiple subgraphs in this way. And let's look at the edge weight reduction. The goal here is to reduce the weight of less relevant edges, especially as the model goes deeper. At each layer, we compute a reduction rate for every edge using an MLP over the concatenated embedding of the connected nodes. And this rate is scaled by a layer number in green, so higher reduction rates or deeper layer reduce edge weights more aggressively. We apply this reduction to the global graph and each subgraph at every layer. And then we perform message passing for the global graph and each subgraph using the adjusted edge weights. And then for each node, we combine the results using the relevance score as weight, so that more relevant subcommunities contribute more to the final node embedding. And this updated embedding is then passed to the next layer. And after we perform message passing for all layers, we aggregate the embeddings across layers to get the final user and item representations. Finally, we compute the preference score of a user for each candidate item using the inner product of their final embeddings. This score is used to rank items and generate the top N recommendation list. We train our model with the BPR loss, which is widely used in recommendation. This is a pairwise ranking loss that encourages the predicted score of a positive item to be higher than that of a negative score for the same user. For the experiments, we use 3 data sets across different domains: the Kindle Store, Yelp, and MovieLens. And each user's interactions are split into 8:2 ratio into training and test sets. And we use 3 metrics: precision, recall, and NDCG to evaluate the recommendation accuracy. First, we assess how well our model addresses oversmoothing by varying the number of GCN layers from 1 to 7. Here, we additionally report MAD on the right, which indicates the degree of oversmoothing. And for all metrics, the higher, the better. And while the baseline models in green and yellow suffer from significant performance drop with the increase in layer numbers, our model in blue is more robust, as it maintains higher performance, especially in deeper layers. And it shows its resilience to oversmoothing. And to evaluate the generalizability of our method, we apply it to 3 widely used GCN backbones: the light GCN, GCCF, and NGCF. In the figure, yellow lines show the baseline backbones, and the green lines show the same models enhanced with a previous method that tackles oversmoothing, and the blue one is ours. In all 3 cases, our model not only improves the performance, but also shows more stability at deeper layers, again highlighting its effectiveness in reducing oversmoothing. We also compare reduced GCN with a wide range of baselines, including the autoencoder-based, GCN-based, and some previous methods that addresses oversmoothing. And our model generally achieves the best performance across all datasets. Next is the ablation studies. On the left, we test the effect of removing edge rate reduction or neighborhood reduction. We see that removing either one causes performance to drop, and NR, the neighborhood reduction, it appears to be particularly critical. On the right, we test the importance of our adaptive subcommunity construction. And here, overlapping means enabling each node to belong to multiple subcommunities instead of just one. And the results show that anchor-based clustering shows better performance than the random clustering by preserving the semantic coherence within each subcommunity. And allowing nodes to belong to multiple subcommunities is essential for capturing diverse user preferences. To summarize, we proposed reduced GCN, a generally applicable method to mitigate oversmoothing in graph-based recommendation by learning to reduce message passing from less relevant nodes or edges. So this is the end of my presentation, and thank you for listening.